We're just constantly bombarded with this existential dread about the physical cost of artificial intelligence.
Oh, absolutely.
I mean, you see these headlines about tech giants looking to reopen decommissioned nuclear power plants or warnings that AI queries use like 10 times the electricity of a standard web search.
Right.
The anxiety is palpable. There's a very real fear that these massive data centers are just going to drain our public utilities dry and cause rolling blackouts.
Yeah, that's the prevailing narrative right now.
Exactly. But what if we have that narrative completely backwards? Like, what if instead of breaking the power grid, AI data centers might actually be the missing puzzle piece required to save it?
I mean, it is a massive paradigm shift. We have traditionally viewed these hyperscale facilities as just pure parasitic loads.
Right, just sucking up energy?
Exactly. They pull energy, they generate an enormous amount of heat, and the local utility just has to absorb that impact. But the internal telemetry of what's happening in these new computing architectures, well, it completely rewrites that relationship.
And that is exactly what we are getting into today. We are doing a deep dive into an internal engineering presentation that honestly just completely blew my mind.
Yeah, it's a fascinating document.
It really is. This comes from the SuperMicro Innovate APAC event that was held on June 1st. 3 experts, Trent Prestigar, Kevin Culp, and Robert Davidoff, presented a deck with a title that basically gives away the ending.
It does, yeah. Turning AI factories into virtual power plants.
Right. So we are going to unpack how the tech industry is trying to turn their biggest liability into a dynamic asset. And for you listening, don't worry, we're going to translate the dense engineering schematics so you can actually understand the mechanics of how this all works without needing a degree in electrical engineering.
Which is good because the presenters, they kick things off by defining the current threat landscape, and they use very specific terminology.
Right, let's get into that. What do they call it?
They describe modern AI data centers as the largest, most volatile loads on the grid. And that word volatile is really the piece that grid operators are struggling to model right now.
Okay, let's dissect volatile here.
Yeah.
Because we've had massive AWS and Google Cloud facilities running the internet for over a decade now. What makes an AI factory fundamentally more erratic than a traditional cloud server farm?
Well, it really comes down to the fundamental nature of the math.
Okay.
Traditional cloud computing, hosting websites, streaming video, managing databases, it's statistically predictable.
Because it's just human behavior.
Exactly. You have millions of independent human users, and their random activity averages out into a relatively smooth curve of power demand, when peak traffic hours are.
Right, like everyone gets home from work and turns on Netflix.
Exactly. But AI training, however, is a unified, highly synchronized mathematical operation. You have tens of thousands of GPUs acting as a single coordinated brain, crunching massive matrices of data.
So we're all working together at the exact same time.
Yes. When a training epoch starts, every single one of those chips ramps to maximum utilization in a fraction of a millisecond.
Wow. So instead of a steady, predictable hum of human internet traffic, it's like a coordinated, instantaneous shockwave of power draw.
That's a great way to put it. And the reverse is also true.
What do you mean?
Well, when that training cycle hits a synchronization point, which is when all the GPUs have to pause to share their calculated weights and biases across the network, they suddenly idle.
Oh, right. Because they have to talk to each other.
Exactly. And when they do, the power draw just plummets. This creates an incredibly violent sawtooth pattern of power consumption. The facility is swinging by tens, sometimes hundreds of megawatts in the blink of an eye.
Hundreds of megawatts. It's insane. Which I guess brings us to the second part of their warning. The presentation points out these massive loads are the least visible to grid operators.
Right.
And this is what I don't get. If I have an industrial facility pulling that much juice, why wouldn't the power company see those swings happening in real time?
Because legacy monitoring systems simply lack the temporal resolution.
Temporal resolution meaning they're just too slow.
Exactly. The systems managing our public grids were built to measure gradual shifts, air conditioners kicking on during a hot afternoon. They operate on a delay, pulling data every few minutes.
Oh, wow.
Yeah, so by the time a grid operator's dashboard actually registers that a massive power spike has occurred at the local AI facility, the physical infrastructure has already absorbed the blow.
It's already happened.
Right. If the grid was already near capacity, that delayed visibility means transformers blow and neighborhoods lose power before anyone can even react.
Okay, let's unpack this for a second. Yeah. It's like having a giant, unpredictable industrial factory plugged into your local neighborhood's power lines. But the power company has a 10-minute delay on their monitors.
That is exactly what it's like.
By the time they see a power spike, the lights on the whole block have already blown out. But that just begs the question. I mean, if we have self-driving cars parsing gigabytes of visual data per second, why can't a multi-billion-dollar data center just send a real-time signal to the power grid? Why can't they just communicate better?
Well, the root cause isn't a lack of broadband or anything like that. It's actually a structural failure in the historical evolution of data centers.
How so?
The SuperMicro deck refers to this as legacy silos. We have to remember how these buildings were built over the last 20 years. They were physical and digital patchworks.
Like cobbled together over time?
Yeah. A real estate developer built the shell and the power routing. An HVAC company installed the cooling, then a tech company moved in and racked up the servers. They never had to talk to each other because historically the power draw was steady.
I see. So you end up with completely isolated domains just sort of living under one roof.
Utterly isolated. I mean, the deck lists them out. You have the BMS, which is the building management system, the power systems, and the cooling infrastructure.
Okay.
And those sit entirely apart from the GPU management, the grid systems, the facility operations, and the workload orchestration.
Wait, so the software telling the GPUs to do the math is physically and logically walled off from the software running the air conditioning?
Completely walled off. There is a total lack of unified standards across these domains. The presentation highlights this catastrophic alphabet soup of competing protocols that are just failing to talk to each other.
Oh no, like what?
Well, on the IT management side, you have REST APIs, Redfish, SNMP, OpenBMC.
Okay, standard networking acronyms.
Right. Then on the compute side, where the actual chips are, you have NVIDIA hardware communicating via NVL and CEDA, or maybe AMD hardware using SCC and ROCm.
Yeah, and those are incredibly complex, high-speed software languages designed to manage massive data throughput in microseconds, right?
Exactly. But here is the critical failure point. The building itself, the massive chillers pumping water to cool the racks, the power distribution units, they don't speak those languages.
What do they speak?
They rely heavily on an industrial protocol called MODBUS.
MODBUS.
Yes, and MODBUS was invented in the late 1970s for programmable logic controllers in traditional manufacturing. It was basically designed to check if a conveyor belt was moving or a valve was open.
Here's where it gets really interesting for me. It's a literal Tower of Babel. The cooling system, speaking MODBUS, has absolutely no idea that the NVIDIA or AMD GPUs, speaking CNA or ROCm, are about to run a massive AI training run. They are completely blind to each other.
100% blind. The heat is generated instantaneously by the GPUs, but the cooling system only reacts after the ambient temperature in the room physically rises enough to trigger a sensor.
Oh man, so it's entirely reactive.
It's an entirely reactive posture, and in an AI factory, reacting after the fact means the hardware thermal throttles, the run crashes, or the localized power delivery fails.
That sounds like an incredibly expensive disaster. So if upgrading the physical chillers and the massive power transformers is too expensive and slow, because I assume you can't just rip out the guts of a live data center.
No, absolutely not.
Right, so how are they solving this communication gap in the software?
This is where the SuperMicro deck introduces their specific solution, which they call the Power Grid Manager, or PGM.
PGM.
They argue that isolated infrastructure is basically doomed. To scale AI, you need a unified, standards-based orchestration layer that bridges the compute, the power, and the grid. PGM is presented as the tool that functions as a critical abstraction layer.
Okay, break down that abstraction layer for us. How is it actually forcing a legacy MODBUS chiller to understand a high-speed CUD GPU? What's the mechanism?
PGM essentially ingests the high-speed telemetry from the GPU clusters and translates it into predictive commands for the facility infrastructure.
Predictive.
Yeah, so think about the workload orchestrator software like Kubernetes, which is responsible for scheduling the AI training.
Right.
Instead of the chillers waiting to physically feel the heat radiating off the servers, Kubernetes tells PGM, I'm going to allocate 10,000 GPUs and draw an additional 50 megawatts in exactly 3 seconds.
So it provides a warning.
It acts as an instantaneous universal translator. PGM takes that high-speed software intent and translates it into a command the legacy building systems understand, spinning up the cooling pumps proactively.
So it turns this fragmented mess into a coordinated real-time system.
Exactly. The entire facility becomes a coordinated, real-time energy and compute platform.
I mean, you can see why a data center operator would pay a premium for that. It saves their hardware, it improves their margins. But let me push back a little here.
Sure.
So what does this all mean for you, The person listening right now, whose main interaction with the grid is just paying their monthly electric bill. Why is a coordinated platform such a big deal outside the walls of the data center?
That is the crucial question. Because once you solve the internal communication bottleneck, you unlock the ability to communicate externally.
Okay.
The AI factory ceases to be a passive, unpredictable drain on the local utility. It actually gains the ability to become a virtual power plant.
A virtual power plant. Let's dig into that because on its face, it sounds completely contradictory. A power plant generates electricity. An AI data center consumes massive amounts of it. How does a consumer become a plant?
It hinges on a concept the presentation calls the utility signal, or ISO-PAO.
The utility signal.
Right. This is a real-time data feed from the public grid operators indicating the current stress level of the electrical grid. To understand why this matters, we have to look at how grids actually work.
Totally.
Our electrical grid operates at a very specific frequency, 60 hertz in North America. If the demand for power outpaces the supply, that frequency drops. If it drops too far, the physical generators at the power plants can actually tear themselves apart, which causes catastrophic blackouts.
So if the grid operator sees a massive heat wave rolling in, everyone is turning on their air conditioning, the power reserves are dropping, and that 60 hertz frequency is starting to wobble.
Yes. Historically, a data center couldn't help in that scenario. It just couldn't react fast enough, and its loads were too inflexible. But with PGM breaking down those legacy silos we talked about, that utility distress signal can route directly from the public grid through the building management layer straight down to the individual GPUs.
Straight to the chips.
Exactly. And this enables a mechanism called dynamic GPU throttling and recovery.
Wait, I have to stop you there. If I'm an AI company paying millions of dollars a month to lease compute power for a critical model training run, I am absolutely not letting the local power company throttle my GPUs. Doesn't cutting power to a massive matrix calculation instantly corrupt the data and ruin the training epoch?
That is exactly what everyone assumes, but that is the genius of this software layer. We aren't talking about unplugging the machine or dumping the memory cache.
We aren't.
No, the data stays perfectly intact in the VRAM. Throttling, in this context, means dynamically reducing the clock speed of the processors.
Oh, I see.
Yeah, the PGM software intercepts the utility signal and coordinates with the workload orchestrator to intentionally stretch the compute cycles. The GPUs pull less power, they do the math slightly slower, but they do not drop the workload.
Okay, if we connect this to the bigger picture, it's almost like regenerative braking in an electric car.
How so?
Well, you hit a steep downhill, or in this case, a grid emergency, so the car changes its physical mechanics. It slows down slightly to absorb the momentum and feed energy back to the battery. It doesn't stop the journey, it just momentarily alters how it consumes power until the road levels out. AI companies can basically act as a shock absorber for the public power grid.
That is a brilliant analogy. Yes, the data center absorbs the stress of the grid without stopping the AI training journey. It drops its power demand by megawatts in mere milliseconds.
And nobody's lights flicker.
Right. And the recovery aspect of dynamic GPU throttling and recovery means that the second the grid stabilizes, the system seamlessly ramps the clock speeds back up. The AI model might finish its training a few seconds later than originally projected, but it successfully prevented a rolling blackout for an entire city.
That is incredible. If the city needs power, they hit pause on training their AI for a few milliseconds, sell that power back. And I mean, the presentation specifically refers to these GPU clusters as, let me find the quote, controllable energy resources.
Yes, that is the most critical quote from the whole presentation. GPU clusters are now controllable energy resources. They are part of the grid's management toolkit now.
But what is the economic incentive here? Utility companies aren't exactly known for getting free favors from massive tech corporations.
Well, the financial mechanism driving this is demand response monetization.
Okay, what does that mean?
Facilities can now monetize flexible load participation. The grid operators actively pay massive industrial consumers for the capability to dial down their usage during peak stress.
Ah, getting paid to throttle down. Because paying an AI facility to temporarily drop 50 megawatts of demand is exponentially cheaper than building a multi-billion-dollar peaker power plant that only turns on 3 days a year during a heat wave.
It is a massive economic win-win. The AI companies get paid by the utility for their flexibility, which heavily subsidizes their astronomical power bills.
Right.
The public power utilities get an instantaneous shock absorber to manage grid stability without building new fossil fuel plants. And the surrounding community doesn't suffer brownouts when an AI company decides to train a new large language model.
We are basically taking the scariest aspect of the AI boom, this insatiable, volatile hunger for electricity, and using unified software orchestration to flip it into a stabilizing force.
Right.
It completely changes the narrative.
It really does. It reveals that our core issue hasn't just been a lack of power generation. A massive part of the crisis is simply a lack of communication.
Yeah.
When the 1970s cooling systems, the cutting-edge compute clusters, and the public electrical grid can all speak to each other in real time, the entire infrastructure becomes remarkably resilient.
So breaking down those legacy silos isn't just an IT upgrade, it's a prerequisite for coexistence.
Absolutely.
As these AI models scale into the trillions of parameters, solutions like SuperMicro's PGM, these unified tools, they are the only reason we'll be able to keep utilizing these technologies without compromising the power we need for our daily lives.
Exactly. It bridges the gap between the virtual demands of artificial intelligence and the physical realities of the power grid. It turns a massive liability into an asset.
This has been a fascinating shift in perspective, but before we wrap up, we always like to leave you with one final thought to mull over something that stretches today's deep dive just a little further into the future based on what we've learned.
Yeah, and considering the implications of this text, if GPU power usage becomes a highly monetized, flexible resource traded in real time with public utilities, it forces us to ask how software architecture itself might evolve.
Oh, that's interesting.
Will future AI models actually be written to follow the sun or follow the wind? Literally pausing mid-thought when a cloud covers a local solar farm and waking back up the second the wind starts blowing again.
Wow. An artificial intelligence whose literal train of thought is dictated by the passing weather outside. That is an incredible image to end on. Thank you for joining us for this deep dive. We hope this gives you a completely different lens to view the next headline you see about AI and the power grid. Until next time, stay curious.